My name is Yevgeny Epifanovsky, and I'm a staff scientist at QChem. Um, Today, it's my great pleasure to introduce to you Professor Martin Head-Gordon. Professor Head-Gordon is Kenneth Pitzer, a distinguished professor in chemistry at the University of California, Berkeley, also a senior faculty scientist at Lawrence Berkeley National Lab. Martin is also a scientific advisor to QChem. Today, Martin Head-Gordon will tell us a little bit about recent developments in density functional theory in his group. Please welcome Martin Head-Gordon.
Thank you very much, Zhenya, I'm very happy to be giving this webinar. So today I'd like to focus on one aspect of QChem's capabilities, which is our very broad and deep range of density functionals, including what we believe are some of the very best new ones available. So today I want to present you some theory and a whole bunch of data to try to answer the question posed in the title: what is the best available density functional for non-covalent interactions, thermochemistry, and barrier heights? So DFT, as you know, is probably the leading branch of quantum chemistry. It differs from wave function theory in that it offers, in some sense, a better trade-off between the cost of computations and their feasibility. Wave function calculations have the advantage that if you add more degrees of freedom, like higher excitations in coupled cluster theory, the answer is guaranteed to get better, and those yield what are called theoretical model wave function chemistries. But density functional theory, we have the great advantage that the ground state energy is simply a functional of the electron density, and the great drawback that even though there is only one unknown term in the energy, so 4 lines from the bottom here is the Cone-Sham density functional theory energy, with the E sub t, the kinetic energy, in green because that is known exactly. The electron nuclear attraction, En, also in green because we know that exactly. The classical Coulomb energy, that's the interaction of the density with itself, also known exactly, Ej. And just one troublesome term, the dreaded exchange correlation energy. And the problem is that we don't know what that is exactly, and furthermore, we don't even really want to know it. In other words, it's too costly. If we could find the exact exchange correlation functional, it would just be like solving the Schrödinger equation. So what we do in DFT is try to model the functional, and better functionals are not always guaranteed to give better results than simpler ones. In other words, we have to assess them statistically instead of knowing that the energy gets more accurate as we do in wave function theory. So when we go looking at the performance of density functionals, we can't just look at 1 or 2 cases. We have to look at hundreds or, if possible, thousands of examples and then try and assess the functionals statistically and thereby assess what kind of trade-offs we have between accuracy and feasibility. So I'll kind of begin the talk with just a little bit of review about how density functionals are classified. And there are various ways to do it, but perhaps the most widely accepted is this Jacob's ladder that is drawn on the right of this slide, which essentially represents rungs that show successively higher evolution of the form of a functional. So we kind of begin in the primordial ooze down the bottom of what is called the Hartree world, where electrons don't even have the right spin statistics. And then the first great evolutionary leap in density functional theory is to the first rung out of the ooze. That's rung number 1 in brown there, which is the local spin density approximation. And I'm showing you on the left-hand side the sort of overall framework, the mathematical framework of what the LSDA looks like. It looks like an integration over one electron coordinate. The electron can be anywhere in space, so that's the integral over r. So it's like a one-point function. We're saying here that the exchange correlation energy and the local spin density approximation just depends on an integration over one coordinate over all space, modulated by the value of the density at each point. So it's a remarkably simple thing, even though chemistry is all about the interactions of electrons. In these simplest density functionals, only the coordinate of one electron appears. The influence of all the other electrons is hidden away in the electron density. The second rung in light blue are what are called generalized gradient approximations, and they improve on the local spin density approximation not by changing it to include any non-locality, but to include what we refer to as semi-locality. So instead of just depending on the density at each point in space, the exchange correlation energy density now depends also on the gradient of the density. And in that way, you can detect changes in the density at a given point. And that's what we refer to as semi-locality. And as you'll see in a few minutes, the kind of numerical examples with numerical accuracy associated with GGAs is far higher than that associated with the LDA, and so this was a key step. I'll skip rung 3 for now, although we'll come back to it in great detail later on. Rung 3 in green includes dependence not just on the gradient of the density, but also on what is called the kinetic energy density, which is like a second derivative quantity. It's at rung 4 that the first non-local corrections begin appearing, the first point at which functions that depend on 2 electron coordinates enter, and those are including non-local exchange, thereby giving rise to what are called hybrid density functionals. Hybrid density functionals are a bit like hybrid plants. It's like grafting a piece of wave function theory into density functional theory and hoping that the resulting hybrid has the best properties of both of its parents. Hybrid density functionals do indeed substantially improve the accuracy of non-hybrids at a computational cost, of course. And then finally, rung 5 is where the density functional depends not only on the occupied orbitals, as does a hybrid rung 4, but also on the virtual orbitals. And we won't be talking much about those today. If we pop up some numerical examples on the right, this is looking at the mean absolute error in kilocalories per mole on the y-axis for a bunch of atomization energies. And in red is the local spin density approximation on the right, which has a truly disastrous mean absolute error that is reduced nearly tenfold by the GGA, which is illustrated by B-lip here, and that error is reduced by roughly another twofold by the B3-lip hybrid density functional. So this is just illustrating that these rungs of Jacob's ladder really do affect the overall average errors. Okay, so let me move to the next slide. I'll spend a few minutes just discussing the range of density functionals in QChem. Many codes offer differing capabilities, and one thing that distinguishes QChem is we have an extraordinary range of density functionals. So if you haven't checked out the range of density functionals, we have a great online manual, and if you get bored with my presentation and you open up another window, I encourage you to browse through section 4.4.3 of the manual and have a look at the density functionals that are currently available. There are more than 25 different semi-local exchange functionals and 25 different semi-local correlation functionals. These are either GGA or meta-GGA, as I've already discussed. I put meta-GGA in green there because there is pretty good evidence that I'll show you later that meta-GGAs are just more accurate, so they're in some sense to be preferred. Sometimes you can't separate the exchange functional from the correlation functional, and QChem 4.4 has over 100 different exchange correlation functionals of truly all sorts. Then the next degree of sophistication is the rung 4 non-local exchange. And QChem has at least 3 different kinds of non-local exchange: global hybrids, like in B3-lip, range-separated hybrids, like I'll be showing you later today, where you have 100% of the exact exchange when 2 electrons are far apart, and a much smaller fraction when they're close together, because when the 2 electrons are close together, a semi-local functional can describe the behavior of exchange much more adequately than when 2 electrons are far apart. And finally, screened hybrids. A very important development in DFT over roughly the last 12 years or so is the development of accurate and usable and affordable dispersion corrections, beginning with the damped C6 potentials of Stefan Grimmer, moving through the Becky-Johnson XDM or exchange dipole models and van der Waals density functionals. And again, I put the van der Waals density functional in green because in some sense it's slightly the most sophisticated of these approaches. It's a true density functional. And then finally, QChem's got a whole bunch of double hybrid density functionals that we won't talk much about today because they are more computationally expensive, but they are actually probably the most accurate of all if cost is no object. So when I try to answer the question posed in the title today, I'm going to rule out double hybrids because of their cost. But if cost is not an object, that's probably the best you can do. To dig in a little bit more to some examples of new functionals, these are ones you might or might not have heard of, but in addition to telling you about my own work, I want to point out some of the work of others that's included in QChem. So for instance, Zhengdao Chai's group at National Taiwan University has contributed the omega B97X-D3 functional to QChem, the omega MO5-D functional, the omega MO6-D3, and the double hybrid PBE0-2. The Purdue group at Temple, virtually all of their latest functionals are in QChem, and this is a laundry list too long to read out individually, but suffice to say that I'm not sure that you can run all of these in any other code at the moment. The TrueR group at Minnesota is very active in the development of density functionals, and you can, I believe, you can for sure run the MN12 functionals in version 4.4, and I think we already have the MN15 ones in there. We can check into that afterwards. If not, they'll be in 4.4.1 coming out very shortly. And then there's the Berkeley group, which is what I will now focus on because that's what I actually know about. So I'll tell you about the functionals developed in my group in detail. And this is work done over the last several years, and it's going to come back to revisiting pieces of Jacob's ladder. Here is a nice picture of a playground in Brooklyn, New York, close to where one of my daughters lives. And my co-worker Narbe Mardarosian, who recently graduated with his PhD from my group, has spent the last slightly over 6 years working with me on the development of new density functionals that occur at rung 3 and rung 4 of Jacob's ladder, and that's what we will now dig into for the next roughly half hour or so. It's perhaps good to begin with a summary so that if you get lost in the details, you know where you're heading back to at the end. So I'm going to be telling you about 3 density functionals, and they are organized as the 3 columns of this chart. The leftmost column under the heading B97M-V is a rung 3 functional that we published in 2015. In the middle column, omega B97X-V is a rung 4 density functional, and the right column is another rung 4 density functional that just came out in the literature about a month and a half ago. And it's this rightmost functional that we are probably most excited about, but each of the other 2 has some special features as well. So let's just walk through those features and then we'll dig into them in more detail. The semi-local ingredient, well, is this a GGA or a meta-GGA? It's the part that depends on only 1 electron coordinate. 2 of these are meta-GGAs, the left column and the right column, and omega B97X-V in the middle is somewhat simpler. It's just a GGA. The third row of this table is NLX, which is short for non-local exchange. And that's the exchange that depends on 2 electron coordinates and is able to compensate for some of the errors of semi-local exchange. And there is none of that in B97M-V. Well, why none? Well, that's just so it can be more computationally efficient. So that will be the fastest functional to run is B97M-V, but it will have some errors that are uncompensated for, unlike the 2 right-hand functionals. Then the next row down is the corresponding non-local correlation. In each of these 3 functionals, we don't use Grimmer C6 potentials, we use true van der Waals density functionals, the functional of Vidrov and Van Voorhis, which is called VV10. and you'll see the form of that a little bit later. The thing that makes these functionals different from functionals developed in other groups is that they're designed based on combinatorial considerations, and that means that we define a search space of functionals, and instead of guessing a functional form and training it either based on exact constraints or chemical data, we are going to in fact train a whole swarm of functionals and try and pick the best of them. We call this procedure survival of the most transferable. And so the rank of the linear parameter search space tells us how difficult the search problem is. And so these numbers are essentially the number of functionals we need to search through, and you'll see that the two meta-GGAs, the left and right columns, these are gigantic functional spaces. These have, we like to call these really functional genomes, because it's impossible to search a space whose rank is nearly Avogadro's number squared. You can never do it. The best we can do is, in fact, is search somewhere between billions and tens of billions of functionals, which is really like a drop in the bucket of that search space. But in the middle, the GGA functional, that's a search space on the order of 100,000. You can search that exhaustively. Then the next row down is how many parameters are actually retained after you go searching through, well, up through 75 parameters in principle in the meta-GGA space. Or even larger. So the point is that we retain a fairly tiny fraction of the parameters that we consider retaining. We retain only 12 of the 144 in the meta-GGAs. We retain 10 of the 16 in the GGAs. Anyway, so that's the outcome. How do we get there? Well, firstly, let's just let me walk through what we're hoping to achieve. Better accuracy for many real-world problems. The asterisk is to remind me to tell you that we will never get better accuracy for all real-world problems. So these are not, strictly speaking, universal density functionals, because the functional form isn't flexible enough. They're good functional forms. They're good for easy chemistry, but that means there are some limitations. Well, there are two main limitations. One is self-interaction error. So this is the error associated with non-locality in exchange. It's only partly compensated for, and that leads to remaining errors. And the other one that's important is strong correlation, where a genuinely strongly correlated problem cannot be well treated by these functionals. That leaves easy chemistry. But fortunately, in my opinion, about 95% of chemistry is easy, and so most problems can be well solved. And then there's one more issue: how many parameters should you retain? And we're going to ignore the strong correlation issue and look and see how well can we do making semi-empirical density functionals that are really useful for chemistry. Okay, so I already told you we're going to define a search space in which functionals will, a whole swarm of functionals will be trained. We try and be very data intensive in this work, so we use, in the end, nearly 5,000 benchmark values to train the most recent of these functionals. And when I say train, we actually have to be careful here that only about 20% of the data is actually used for training. The vast majority of the data is used for testing, because after all, if we're going to train billions of functionals, a better least squares fit is not an indication of a better functional. Indication of a better functional is better performance on test data after training. So that's why almost all of our data is used for testing. That's actually how we are able to then decide which is the best functional to keep. Well, the best functional to keep is the one that is most predictive, that performs best on the test data. And in the end, we balance those considerations, and we also try to use what could be called an Occam's razor criterion, which is that you can, to a certain point, keep adding parameters and obtain perhaps tiny improvements, but we consider that the addition of an extra parameter should be associated with a chemically noticeable improvement, not an infinitesimal improvement. Okay, so that's the overall layout of the design procedure. This next slide is incredibly dense. You can read it if you put a magnifying glass up to your screen, I guess. It's just to quickly it's just to show you the diversity of data used. Broadly speaking, we've got NC, that's non-covalent data, and we partition it into easy and difficult. We never train on difficult problems because in that way, at best, one could get the right answer for the wrong reason. If you train on a problem that has strong self-interaction effects, but you don't have a functional form that can really properly describe it, at best you get the right answer for the wrong reason. So we only test on difficult data. We never train on it. I is for isomerization energies, TC is for thermochemistry, and BH is for barrier heights. And so we have a lot of everything. This is the largest data set ever used to assess density functionals. I now want to just dig into this. Next slide comes really back to the Jacob's ladder construction. I just want to show you the inside of the functionals. EXC, well, that's the one unknown term of the density functional, and it's now split into up to five contributions. The first three in black are the semi-local ones. And for the GGA in the green box on the screen, the GGA, it's derived from the exchange correlation energy density of the LSDA multiplied by a factor in blue that we call the inhomogeneity correction factor that either attenuates or amplifies the exchange correlation energy at each point in space. And the variable u in that expansion depends, well, of course, on the density gradient. That's what makes it a GGA. On the other hand, if we look at the meta-GGA, we have not a one-dimensional Taylor-like expansion, but a two-dimensional Taylor-like expansion, where the second degree of freedom W contains in it, it's a dimensionless variable that has dependence on the kinetic energy density. You can begin to get an idea about the combinatorics, right? If we truncate these expansions at n equals 4, which maybe is a reasonable thing to do, we would then have 5 parameters in the blue expansion, but 25 parameters in the red expansion. And then we'd have to multiply by 3 for the 3 different terms of the exchange correlation energy that have to be represented this way. And so that's where the greatly different dimensionality of the search spaces come from. So for the GGA, the second last line, we have 5 times 3, which is 15 possible parameters. Each one could be included or excluded, so that's 2 to the 15th possible functionals. That's the number on the order of 10 to the 5th. For the meta-GGA, we're on the order of Avogadro's number. We actually go up a little higher than m equals 4. That's the origin of the functional genome. All right, the remaining pieces are the non-local corrections, and one of them is the non-local range-separated exchange. So you can glance at this equation and see that there are integrals over the coordinates of 2 electrons, so it's non-local. And secondly, it has the one particle density at R1 and R2, and 1 over R12 with 100% long-range exact exchange and a variable fraction controlled by one more parameter Cx of short-range exact exchange. Then in purple is the non-local correlation, also an integral over 2 spatial coordinates, because dispersion really is a correlated fluctuation between the density at one point r and a second point r prime. And the VV10 functional builds this in through a 6-dimensional quadrature and includes a kernel, capital theta here, whose asymptotic distance dependence is r to the minus 6 to capture dispersion. So those are the building blocks, and that's why these functionals are capable of being great for non-covalent interactions. They're capable of getting easy thermochemistry, and particularly if the exact exchange is included, they're capable of doing well for barrier heights. But they're not capable, because of this design, of being really good for very strong self-interaction sensitive problems, or in particular strong correlation. All right, well, we try and work close to the complete basis set limit in training and in testing and in applications. This actually turns out to be highly desirable. If you use a smaller basis set, you get clearly less good results. We fix the nonlinear parameters initially, and then we inspect the huge swarm of trained functionals by making XY plots, where on the y-axis is the RMS error in, for instance, the test data. And on the x-axis is the number of retained parameters, and we're essentially looking for either a flattening out or a straight out minimum in the y versus x plot. This is then the process that has led to the training and testing and selection of 3 functionals, and Narbe has trained nearly 1 trillion density functionals. He is the trillion density functional man, but we only report 3 of them. Just to give you a little idea about how we do, how can a drop in the bucket, that is billions of functionals out of Avogadro's number, how can we have any idea that we've maybe found the best functional? So this slide is to give you some idea of how we do the incomplete search. The trick is basically to firstly search as many free parameters as we can exhaustively. So it turns out we can do up to 7 free parameters, and then with 7 done, we then look to see which parameter occurs, for instance, in roughly the top 100 or 1,000 best performing fits. And then we force the inclusion of that parameter in a new search that goes further. We don't force its value, we just force its inclusion. So for instance, the exchange terms that are linear in the spin density gradient and linear in the kinetic energy density are the first ones to be fixed. And you can then see that if you fix CX01, we can then do a search up to 8 free parameters, but the one that we are forced to include and the 7 extras we can now choose. And this way we bootstrap ourselves up. We do a bunch of things to make sure that we're only looking at good candidates. So for instance, we filter out functionals with unacceptable grid sensitivity or unphysical features like a negative inhomogeneity correction factor for exchange, which should be aphysical. We reevaluated our orbitals from the LSDA to now best 8, and we search further, and eventually you get plots of the form that you see on this screen. This is an example for B97M-V, showing as you go from 11 parameters, the lowest RMS error in testing that one can achieve is about 4.97 or so. As you go to 12 parameters, it drops down to 4.83. As you go to 13, it approaches 4.8, then begins to bounce around, indicating that we have reached the predictive limit, we believe, for this functional design. And so you look for the elbow in this kind of curve, and the elbow, we believe, occurs at 12 here. We choose a 12 linear parameter form. And we've done the same thing in each of the 3 different cases. This next slide is just to illustrate the parameters that you get for the latest functional, omega B97M-V. It's 12 parameter range separated hybrid meta GGA with VV10 dispersion. And the parameters all fit nicely on one slide. You can stare at them for a while, but the first point to make is that they're all on the order of 10 to the 0 to 10 to the 1. There are no big values for those parameters. That makes the inhomogeneity correction factor smooth and is really a precondition for transferability. And the next thing one can see staring at those is that terms are skipped in those Taylor series-like expansions. For instance, if you look at same spin correlation, 0, 0 occurs, 1, 0 occurs, 0, 1 is missing, 2, 0 is present, 0, 2 is missing. So the combinatorial design process has selected most of the very low order terms, but then a small and apparently exclusive selection of the higher order ones that are in fact helpful. It's important to say that there are probably thousands or even millions of alternative choices for the functionals that would perform almost as well. In other words, we finish up with a very flat search space, and so while it's sort of tempting to believe that what I'm reporting to you is the very best possible, the very fittest, it's really actually more of a representative of the fittest. And the ambiguity really begins to occur in those higher order terms, which are included and which are not included. All right, so now it's on to data. And the rest of this talk is now about assessing across roughly 5,000 data points the new functionals, which are labeled in green on this slide, so B97M-V, the rung 3, omega B97X-V, the GGA-based rung 4, and omega B97M-V, the meta-GGA-based rung 4, against now a range of existing density functionals that are shown in blue. And we'll kind of walk our way up Jacob's ladder starting from rung 2. So PBE-D3 is the first functional we'll look at, and it's really a non-empirical, well, perhaps there's one empirical parameter there, which is the mixing of the D3 tail, but it's essentially a non-empirical functional. Then walking across the column entries, NC non-covalent, D for dimers, C for clusters, you can see that PBE-D3 has an RMS error of about 0.5 kcal per mole, so that's the 1 sigma width of the error distribution for non-covalent dimers, about a 6 kcal per mole for non-covalent clusters, so 10 times bigger. Moving on to isomerization energies, 0.7, thermochemistry 10, barrier heights 10. So that's rung 2. As an existing representative of rung 3 and a pretty good representative, we'll start with MO6L. So this is a local, no exact exchange, meta-GGA. That's why it lives on rung 3. It has 34 empirical parameters, so that's rather a lot. But you can see that in some sense those empirical parameters are doing something on our test data, which is that we are break even with PBE-D3 for non-covalent dimers, roughly. A factor of 2 better for non-covalent clusters, many-body non-covalent. Break even on isomerization energies, and something like 1/3 better for both thermochemistry and barrier heights. And so that's really a signature of the meta-GGA, that for easy thermochemistry and barrier heights, they are capable of doing better than a straight GGA. Okay, so now the first comparison against new functionals. So B97M-V, so this costs essentially the same to evaluate as MO6-L, and how does it compare? Well, these are exciting results, and one of the reasons that we are excited about these functionals, it has almost 1/3 the number of parameters, 12 instead of 34, reduces the width of the RMS of the error distribution by more than a factor of 2 for pairwise non-covalent, by more than a factor of 2 for many-body non-covalent, by more than a factor of 2 for isomerization energies, by something like 1/3 for thermochemistry, and by something like 1/3 for barrier heights. So it's just better for everything compared to a good existing rung 3 competitor across all of this data. And so that's exciting. Now let's advance to rung 4, and our rung 4 representative is omega B97X-D. That's a functional that Zhengda Chai and I co-developed in 2007-8. It's a 15-parameter range-separated hybrid with empirical dispersion rather than van der Waals dispersion. You can see it's not as good as B97M-V for non-covalent pairwise interactions, break even on many-body non-covalent, considerably poorer on isomerization energies, break even on thermochemistry or a tiny bit better, and then one significant difference, which it is much better for barrier heights. That last column, the BH, that's the role of exact exchange, because barrier heights are somewhat self-interaction sensitive, and including exact exchange range-separated style makes a significant difference there. We can now compare omega B97X-D, the 2008 functional, against omega B97X-V, virtually the same design except for 2 distinctions. One is the combinatorial search, the other is the replacement of the Grimmer C6 potential, the -D, with a true van der Waals functional. And the net result is well worth the effort, actually. We see a 1/3 reduction in the number of parameters. So in other words, we included some non-essential parameters in omega B97X-D, something like a 1/3 reduction in the RMS error for pairwise non-covalent interactions, and also many-body non-covalent, a factor of 2 reduction for isomerization energies, and break even on thermochemistry and barrier heights. So now let's switch from hybrid GGAs to hybrid meta-GGAs, and we'll use MO62X from the TrueLog group as a good representative of existing hybrid meta-GGAs. It's a 29 parameter functional. If we scan across the columns here, we see that it is not competitive with our new functionals for the non-covalent interactions, but is very competitive for thermochemistry and barrier heights. So that's the sort of short summary of MO62X. And then if we look at omega B97M-V, so this is now our range-separated hybrid meta-GGA with VV10 correlation. Well, it's exciting to compare this with MO62X because it wins for everything. Great reduction in the number of parameters, halving the RMS error distribution for pairwise non-covalent, 1/5, width for many-body non-covalent, roughly half for isomerization energies, and something like 1/3 better for both thermochemistry and barrier heights. So this slide is really the take-home message about easy thermochemistry. This next slide is just updating the data to include the new Minnesota density functionals. So earlier this year, the TrueLog group introduced MN15-L as a new semi-local functional. So that's on rung 3, just like MO6L is on rung 3, just like B97M-V is on rung 3. So that bold red line is to divide semi-local functionals above from those that have exact exchange below. And MN15-L is, well, largely quite poor for non-covalent interactions, but is more successful for thermochemistry and also more successful for barrier heights. But interestingly, again, across all of these 5 categories, it does not beat B97M-V on any. So we are led to the conclusion that for relatively easy chemical problems, B97M-V is the best semi-local functional available for main group chemistry. By the way, none of our data includes transition metals, and that's one area that has to be addressed in the future. Okay, then going down the rest of the slide, we can now compare MO62X against MN15 and see how the TrueLog group has progressed in design of their new 2016 global hybrid meta-GGA, a new rung 4 competitor for both MO62X and our new functionals. And it has 59 parameters, so this is a significant increase over MO62X. But you can see that relative to MO62X, it is at least break even and in some ways an improvement. It's not an improvement really for non-covalent interactions. It's slightly poorer for thermochemistry, but it's a significant improvement for barrier heights. So the rightmost column, that 1.98 number for MN15, that's really the best result that functional has. And again, it does not surpass our omega B97M-V in any respect. So in this sense, a less empirical functional, only 12 semi-empirical parameters, is outperforming the 59 empirical parameter functional by a fairly wide margin. Okay, so far everything has been easy. So now comes the truth test, which is we need to look at the difficult cases. So these are ones that are self-interaction sensitive or multi-reference or both. And so we'll go back to the same functionals that I was showing you 2 slides ago. And for non-covalent dimers, we have the easy numbers reproduced from 2 slides ago. Take a deep breath and have a look at the difficult numbers. These are difficult to look at because they're so much worse. So PBE-D3, you grow the error by something like a factor of 8 or so, MO6L a factor of 3, B97M-V a factor of 8 or 9, omega B97X-D a factor of 4, omega B97X-V a factor of 6, MO62X a factor of only 2. So MO62X is the best of these for these difficult cases. and omega B97M-V a factor of 9 again. So huge degradation in the difficult cases. Isomerization energies, well, it's the same story played back again, which is that we have lots of trouble here. The difficult cases are between, well, sometimes more than 10 times worse than the easy cases, because our functional form is not capable of correctly describing that kind of problem. Easy thermochemistry against difficult thermochemistry, also a big problem. So the take-home message here is that while the new functionals as well as the existing functionals are great for treating easy problems, they do begin to break down and degrade when self-interaction or strong correlation is at play. We can also put the Minnesota functionals onto the same slide, and you can see that Mn15 performs quite well for difficult non-covalent dimers. For isomerization energies, the performance of all of them is really quite marginal. And for thermochemistry, much the same story. So this is really the main caveat that has to be given about this. So now let me wrap up and leave some time for questions. So I've told you about 3 new functionals, one that we introduced in 2014, one in 2015, and one in 2016. These are great functionals, particularly the 2016 omega B97M-V for easy thermochemistry, easy non-covalent interactions, and barrier heights, and also the 2015 functional, which is we believe the best available non-covalent, the best available semi-local functional. There are 3 caveats to note here. The first note is that to get these good results, it was essential to use large basis sets. You can't use small basis sets and get the kind of accuracy that I've shown you. The second caveat is that no transition metal systems were involved in either training or testing. I'm optimistic that our functionals will work quite well on transition metals containing systems, but there is simply not enough good benchmark data available to make an assessment of that now. And the third caveat should be clear in your minds from the last 2 screens, which is that things really go bad in the difficult cases, so you should never forget about the limitations of density functionals. All right, well, I owe an enormous debt of gratitude to my co-worker, Narbe Marderosian. This was, as I told you, more than a 6-year project, and after the first 2.5 years, we really had no useful results. So often in science, you have to persist and you have to make mistakes in order to move forwards, and it's a complete pleasure to acknowledge that this project would have been impossible without Narbe Marderosian, and I'm very proud of what we've done together. The next acknowledgement is to QChem. All of our development of functionals is done entirely within either the standard versions or specially modified versions of QChem. You can run these functionals in all of them in version 4.4. You can also run them in the newly released version of Spartan 16. And I guess it just remains for me to give you a few places that you can look for extra information about QChem. We've had quite a few of these webinars. You can browse them all on YouTube. You can go to our website. I particularly encourage you to look at the online manual, because if you're interested in density functionals, that's where you find the latest information. The online manual is the ideal place to look. If you have not played around with QChem yet, one of the easiest ways to get started is to download IQMol from www.iqmol.org. And you don't even need to have QChem, because IQMol will build simple jobs, small jobs, and run them on the server at QChem headquarters. In fact, just close to Evgeny and Zhengting's offices. So you can try that, and if that gets you intrigued, you can get a proper demo license. You can also read, of course, about a lot of the developments. There's a review of QChem 4, but the online manual even goes beyond QChem 4. And well, I've been Gaussian free since 1993. I encourage all of you guys to be as well. Being free is a good thing, and at QChem we encourage people not just to use our code, but also to be developers, and we don't insist on any sort of weird exclusivity or strange license agreements like Gaussian does. And if you do all that, you could be on the road to better chemistry, and those are a couple of IQML screenshots to finish with. So at that stage, I will wrap up and take any questions you might have.
Thank you, Martin, for the fascinating talk. Have you looked at the shape of bond dissociation curves with the functionals?
To some degree, yes. So the way in which DFT breaks bonds is by spin polarization. Spin polarization is something that it works very well as you go all the way to dissociation, and also works very well as you begin to dissociate. There is what is called a recoupling regime, where the bond is half or two-thirds broken, that is essentially a strong correlation problem. And what DFT, or any kind of DFT, including our functionals, does is it is accurate at the two endpoints, and it traces a smooth curve that joins them up. But it is not necessarily accurate in the recoupling region, because that's a strong correlation regime.
Thank you. The next question is, I guess, about computational performance. Could you comment on the relative performance of the three functionals?
Let me comment on the relative computational costs, I guess, which I presume is what's being referred to. So the least expensive functional to run is the one that has no exact exchange, because that enables a lot of QChem's fast algorithms for the Coulomb energy to be used very effectively. If you compare B97M-V to, say, MO6-L, there is a small amount, typically less than 10% to 20% extra cost associated with evaluating the VV10 non-local correlation functional. So in other words, compared to a meta-GGA, a semi-local meta-GGA that you might be used to running right now, the extra cost is quite small. If you then go to the hybrids, well, QChem's got some nice tricks to make range-separated hybrids no more costly than regular hybrids, so that's an algorithmic advantage that QChem has had for several years, and that means that omega B97M-V costs, well, a little more than omega B97X-D or omega B97X-V, because you need to use a slightly bigger quadrature grid to reliably integrate a meta-GGA as opposed to a GGA. But for a big molecule, those are not the rate-determining steps, and eventually the costs become very similar. So if you can already afford to run a large basis density functional, you can afford to run these. If you can't afford to run a large basis density functional and you're forced to use a basis like 631G star, the only honest answer I can give is that these new functionals do not offer a big advantage over something like B3-lip or MO62X in a small basis like that. You need to go towards the basis set limit in order to see the really beautiful shrinking in the error distributions that I showed you earlier on.
Thank you, Martin. The next question is about omega B97X-V and its in comparison with the earlier omega B97X-D. Have you looked at what actually causes the change in performance? Is it the exchange correlation functional itself, or the treatment of dispersion?
It is primarily the treatment of dispersion. You might have got a hint of that from the results that I showed you, where if you looked at thermochemistry and barrier heights, the new functional, despite having 1/3 fewer parameters, was virtually identical to the old one. But everything that was to do with non-covalent interactions was significantly improved. This shouldn't be too surprising, because if you think about the -D correction, every oxygen atom is treated the same regardless of its environment. But in the VV10 non-local correlation functional, every oxygen atom is treated differently according to its local electron density. And that enables the larger dispersion associated with a partial negative charge to be accurately captured in the -V form, whereas at best the -D form is kind of an awkward compromise, it's a bit like saying one shoe size fits all. Well, at a first approximation, all human feet do lie within a range of sizes, but we certainly don't want one shoe size. And so the way in which the non-local correlation functional adapts to local environment is really the key advance. That's the main reason for improvement.
Thank you. The next question is, can you comment on why Minnesota functionals give slightly different results in different implementations, in different software packages?
I guess I'm not sure I can, except to say that the Minnesota functionals are quite sensitive to grid. Some of them are more sensitive than others. The MO6 functional, for instance, is quite sensitive to grid. So if one runs, for instance, with QChem's default grid, which is it's probably simply too small to accurately integrate the Minnesota density functional. So if one wants to really compare results from one software package to another, it's important to wind up all tolerances to be tighter than defaults and to make the quadrature grid a lot bigger than the defaults. For instance, Narbe and I showed in a paper published a few years ago that it's nearly impossible to reach a complete basis set limit for intermolecular interactions with the Minnesota functionals, the MO6 generation functionals. And MN15 is less grid sensitive than earlier Minnesota functionals, and in that sense is a step forwards, even as it increases the number of parameters by nearly a factor of 2. So the better behaved the functional, the less sensitive it should be to different numerical details in different packages. And so we would hope that MN15 will be more reproducible between different packages than some of the, well, in particular, say, the M11 functionals are quite sensitive, some of the MO6 ones are also very sensitive. So tricky question. That's all I can really suggest.
Thanks. Yeah, that will be also my guess that it probably has something to do with the defaults set in each package and the algorithms that are used. So, and I wanted to make a note in passing that the latest Minnesota functionals, MN15, are available in the latest version of QChem. So the QChem 4.4.1 should be available to the users shortly. The next question is, have you assessed the accuracy of the new functionals on excitation energies for core valence, Rydberg, and charge transfer excitations?
The answer is no. We should do that at some point. We haven't done it yet. One reason for not being too excited about doing it is that I don't think there is really anything in the design of these functionals that should lead us to expect significantly better performance in TD-DFT. In other words, the things that are most important sources of error in excitation energies computed by TD-DFT are the details of how you do range separation, and therefore how much error you have in charge transfer excited states. So I don't expect that our new functionals should be significantly better than existing ones for excitation energies. When I go back to my catalog of DFT problems, excitation energies are strongly self-interaction sensitive, many of them, and therefore they are not necessarily in the category of easy chemistry. But we will check that out at some point soon and hope for good results, but it'll be interesting to see.
Thank you. And I guess one last question is, are frequency calculations available with the new functionals?
Well, analytic gradients are available. The analytical second derivative of the VV10 component of the functionals is not implemented in the current version of QChem and is a tricky project. So when one does frequencies, QChem will default to doing finite differences if you need to compute all the frequencies. If you have optimized a geometry and you want to know, is it a minimum or a saddle point, QChem has a neat new algorithm in it that can answer that question without computing the full force constant matrix. And that's what we would recommend for characterizing stationary points. In other words, if you've found a transition state and you want to know, is it a transition state? In QChem, you no longer have to compute the full force constant matrix, which is very, very costly for a big molecule. And so that algorithm, the Hessian free determination of the character of stationary points, can be used directly with all the new functionals.
All right. Thank you, Martin, for your time, for answering questions, and for the beautiful presentation. I guess at this time, we'll wrap up this webinar.
This concludes our webinar. We would like to thank Professor Martin Hennig-Gordon for his excellent presentation, as well as Zhinting Gan or Evgeny Epifanovsky for organizing, moderating, and running this webinar. Should you have any questions, please feel free to contact us by emailing either Zhinting or Evgeny at the email noted on your screen. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.